Okay, you're right. Welcome to your tutorial on 3D Pythagoras. Today we are going to have a look at the way in which we can use Pythagoras in order to solve problems that involve 3D objects. So, many real-life situations involve three-dimensional shapes. Just to confirm, three-dimensional shapes are shapes with length, width and height. So boxes here, or I've also got an example of a pyramid, okay? So there's length, there's width and there's height. So we're no longer looking at just flat shapes. We're going to have a look at 3D shapes. Now before we do, there's a really important note to make. The important thing about when we're looking at 3D shapes and we're trying to find out right angles, they might not necessarily look like right angles when they're in a 3D shape. So it's kind of really important to redraw sections of our three-dimensional shape into a flat, into a two-dimension, where the right angles can be seen accurately. So if we have weird shapes like this, it's a 3D shape, we can't easily see that there could be a right angle going through maybe down here and in this section. So in order to solve this problem, we usually like to redraw them, okay? So what we'll be doing today is a little bit of redrawing of shapes. So let's have a look at our example. Our example says, using Pythagoras' theorem, find the length of AG in this box. Now, let's have a look at our diagram. A starts up in this top corner, G ends in this bottom corner. So if you imagine we're getting a knife, we're technically going to cut through the middle of the box here. Okay, we're going to go down here and we're going to go along here. Now my triangle looks a little bit funny at the moment because it's on an angle. So I'm going to need to redraw it. And that's why I've redrawn it over here. Now this redraw that I've done, okay, I've only labelled one dimension, okay, because that is all I have. Now we're encountering an issue. If I only have one dimension, so if I only have the 6, I know it's 6 tall because the 6 over here means the other side must be 6 as well. If I only have one dimension though, how can I work out another side length? The answer is, well, I can't. I can only use Pythagoras to work out a side length if I have at least 2 of the other sides. So what I'm going to have to do is I'm going to have to work out E to G before I can work out A to G, which is what the question wants me to do. Okay, E to G. How could I work out that? Let's have a look at this diagram. E runs to G there. Is there any other right-angled triangles that have that same common side, E to G? Is there any other right-angled triangles in this diagram that also share that same side? When I look a bit more closely, I realise that there's a triangle that goes like this, a right-angled triangle, that it goes along there, and it also, oops, I didn't do it close enough, but it also shares that E to G side. I know that one side of this triangle is 5, and I know the other side's 10. So I know that I will be able to use this other triangle to find E to G. Then, once I've done that, I can then use that answer to get A to G. Okay, so let's use this other triangle first. This other triangle is 5 by 10. So I'm going to redraw that. I've just got rid of everything. This is the triangle that also shares the E to G side. Okay, and I'm going to redraw that. It goes 10 across. Oh, sorry, that's a bit of a dodgy drawing. Let me do that again. Okay, it goes 10 across. Whoop. 10 across from F to E. Okay, it goes 5 up and it goes across there. Okay, this is the one I'm after, E to G. That's the important one, E to G. Okay, F to E I get given. F to E is 10. I know that because the other side is 10. G to F is 5. I've put that in there. I'm after G to E. Now, if my right angle is in here, I know there's a right angle in here because it's a rectangle. That must mean that these are my two short sides and this side's my long side. So following Pythagoras' theorem, c squared equals a squared plus b squared. Okay, I'm looking for g to e, which is the hypotenuse. Okay, so c squared equals 5 squared plus 10 squared. Okay, so what's the answer for 5 squared? 5 squared is 25, 10 squared is 100. So it's 25 plus 100. So c squared equals 125. So the box that's coming off the hypotenuse at the moment, and by box I mean the area, c squared, is 125. In order to find that length by itself, I need to find the square root of 125. And when I do that, I get a funny answer with a decimal. So when I type in the square root of 125 into my calculator, I get an answer of 11.1803. I'm going to round that to 2 decimal places. So when I round that, I'm going to get an answer of 11.180, so 18. Well, that's gone off the screen, sorry. I'll redo that. 11.18. Okay, 11.18. That is the answer for this arm here, from E to G, 11.18. So now I have 2 sides. I have E to G, and I also have B to F. So I'm able to use this new measurement now in order to work out A to G, which is what the question wants me to do. So I've popped in 11.18 and I've popped in 6. We've been asked to find A to G. Okay, we've been asked to find A to G. If this is my right angle here, that's going to be my hypotenuse. So c squared, oops, I wrote that really big and I'm going to run out of room, aren't I? Let's do that again. C squared equals a squared plus b squared. Okay, let's sub into our formula. C squared equals 6 squared plus 11.18 squared. Okay, c squared equals 6 6s are 36. Mr. Corsi is going to need a calculator to do the next one. 11.18 squared. 11.18 squared is 124.99. Okay, so c squared is going to equal a total of 160.992. In order to find out c, I need to find the square root of 160.992. Okay, and the answer, when I type that into my calculator, is square root of 160.992. I get an answer of 12.688. Now, rounding that to 2 decimal places, I'll get an answer of 12.69. Okay, guys, and that is it. That is as difficult as it gets. I know it was a bit tricky. I know it was thinking, oh gosh, that's just so many steps involved. But all you have to do is you have to look at it and say, what information do I have? What information can I use?